I will begin with a word of prayer. So, Heavenly Father, we thank you again for your many blessings, and for this class, just help us to glorify you what we do, and just to understand more about the wedge product and how to construct it and work it and all that stuff, Lord. In your name I pray, Lord Jesus. Amen. So, let me get my notes. I think I'm in the 2015 notes again. But I will, try to. I'm not sure. I'm not saying this isn't in the 2017 notes. I just don't know. Okay. Now, so we want to talk about the tensor product, I suppose, but really I'm after the wedge product today, and I want to talk about how to understand the wedge product. I mean, there's different ways to go about this, okay? Like, we could go about it from a completely abstract algebraic perspective and just build it as like a formal product, but we're going to go a different way. For us, they're just going to be particular multilinear maps. But admittedly, there's different ways to go about this. Let me get into it. Anyway, so we had T, let's say a tensor, and we'll just do on V cross V. Let's say R-fold times, okay? So we'll, and I suppose that would make this a what? In our language last time, type what? R0 tensor, I think, yeah. All right. So I'd like to define what I mean by that being completely symmetric or completely anti-symmetric. All right. So in order to do that, I need a little bit of notation. And so, and here the dimension of V is, we're going to assume n. All right. And so sigma n, I think, is just going to be the set of bijections on n sub n, if you like, 1, 2, and so it's permutations. I guess typically in mathematics we just call this what? The symmetric group, right? Sn. Yeah. And so you may recall that if sigma is an element of the set of permutations, then sigma can be written in its disjoint, can be expressed in so-called, cycle notation, right? And in particular, there's a theorem that any permutation can be written as a product of transpositions, right? Which are just two cycles. And you can define, and moreover, the theorem says that any decomposition of a permutation into transpositions, the number of two cycles is an invariant. So that allows us to define the so-called sign of a permutation. And this is either equal to 1 if sigma is even permutation, and it's equal to -1 if sigma is an odd permutation, right? And so even means expressed with even number of 2 cycles. And odd means it can be expressed as odd number of 2 cycles. And again, this is unambiguous because the number of 2 cycles that form a permutation is an invariant up to a multiple of 2, up to a, let's see here. So for example, if we were to talk about sigma, I'll write it this way. Sigma of 1 equals to 2. Sigma of 2, example 1. Okay, sigma of 2 equals to 3, and sigma of 3 is equal to 1. Like a ninja. I didn't even notice him until he's like all the way over there. Let's see here. So sigma, this is not cycle notation, obviously, but this in cycle notation would be sigma equal to 1, 2, 3, right? And is this a even permutation or an odd permutation? Why would you say that? Can you write this as a product of transpositions? What is it?
I forget how this works, but would it be 1, 2?
Wait a minute, aren't you taking abstract algebra?
I took it 2 semesters ago.
Oh, curses. Yeah, well, that'll fade then, won't it? I have the same problem. So 1. All right, so 1. I'm trying to remember how it goes. Let me just try something, see if that works. It may not work, but this makes 1 go to 3. No, that's not what I want. Let's try this again. I'll do 3, 1, 3, 2. Let's see if that works. All right, so I plug in 1, goes nowhere, goes to 3. That's not working. Dang it. What's a stupid trick for that? I can't for the life of me remember. We'll figure it out eventually. If this takes us all class, we will figure this out. Well, these are cycle notation. So if I, for example, here let me just do something like 2, 3, 3, 1. All right? So I start out with 1. Where's 1 go? 1 goes to 3. 3 goes to, so that goes to 2.
Nice.
All right, so now I'm on 2. Where's 2 go? Well, 2 goes nowhere. 2 goes to 3.
Okay.
Then what? Then I go to 3. Where's 3 go? Well, 3 goes to 1. And then we're back again.
Yeah.
Oh, that's kind of funny. I just made up an example. And anyway, now the thing is, this is equal to, of course, like 3, 2, 3, 1. Because the permutation, the transpositions are symmetric in that way. I guess that was the trick. You go 3, 2, 3, 1. So you do the last one, then that one, the last one, then the first one. And that's kind of like a general trick, if I remember right. So you were right. It was even. How about if we do, say, beta equal to, I don't know, 1, 3, 2.
It should be even as well.
I feel like it should be even as well, yeah. Hmm.
So we're just relabeling numbers.
Sorry, something's very troublesome to me all of a sudden. Hmm.
Like those two.
Yeah, there's something I'm confused about here, and I don't want to share. I don't want to give you my confusion, so I won't try to say it. I don't think it's right what I'm thinking.
And if I remember well, permutations with odd length were even, and vice versa.
Yeah, I think that's going to be, if this trick works for this one too, if we can just do this is what, like 2, 3, 2, 1, does that work? So we hit it with 1, 1 goes to 2, 2 goes to 3, okay. That's what we want. 1 went to 3. Then try 3. Well, I hit 3 in here, 3 goes to 2, 3 goes to 2, okay, great. I hit 2 in here, 2 goes to 1. Yeah, yeah, you're right. So that's also even. Cool.
When they can be expressed as a single permutation, if it has an even number of elements, then it's odd, and vice versa.
Well, yeah, I mean, there's also, let's say, like gamma is this one. Well, I'll call it gamma 1. Gamma 2, this one. Gamma 3, this one. Right? And those are, of course, those are all odd, right? So like the sine of sigma equals to the sine of beta equals to 1 in my notation, right? And that's also the sign of the identity, right? So you have 3 even permutations, and you have, these are all odd, right? Okay, yeah, actually this is okay. This is okay. It's really okay. There's something I was hung up in my mind about how things work, so it's okay. Let me try to explain my confusion. So my confusion was with the formula, like for the cross product. So the formula for the cross product, for instance, would be this, like V cross W. I can write it as the sum over I, J, and K of epsilon I, J, K, V, I, W, J, X hat. Funny. Okay, I guess I'm violating my convention, aren't I? And so the thing that was bugging me about this was, I know that epsilon 1, 2, 3 equals epsilon, 2, 3, 1 equals epsilon 3, 1, 2. Those are all 1, versus epsilon 3, 2, 1 equals to epsilon 2, 1, 3 equals to epsilon 1, 3, 2. Those are all minus 1. And I also know that that plus 1 and minus 1 is the sign of a certain permutation. But what what was wrong in my mind was thinking that the index positioning of the Levi-Civita symbol here is the same as the cycle notation down there. That's not what's going on. You have to think about, to understand the interplay here, we got to think about 1, 2, 3, and it's going to, to this, or to this, or to this, or to this, or to that, or to that. That's the permutation. That's the permutation, all right? And so this is the identity. 1 goes to 2, 2 goes to 3, 3 goes to 1. That's the 1, 2, 3. That's the 1, 2, 3 cycle. This one is the 1, 3, 2 cycle. This one is fixing 2 and flipping 1 and 3. This one is transposing 1 and 2. This one is transposing 2 and 3. And so that's why we get +1 and -1. That's the interplay between these two formalisms. So, yeah. Now, of course, I haven't really set out the formalism yet, right? So I'm making a future comment here at the start, which is not the greatest pedagogy, but that was what I was confused about. And it's needless, because it's all consistent when properly interpreted. All right, so here's the definition. T, a type R0 tensor is, number one, completely symmetric. If T of here we go. V1, V2, VR, right, is equal to T of V of sigma 1, V of sigma 2, V of sigma R, all right, for all, a horrible for all. What happened to my for all? For all sigma what? What are we looking at here? Permutations of what?
For all R. I mean, I. Sorry.
So we're permuting 1 through R, so it's for all sigma in, you can either say sigma R, or if you want to use standard math lingo, S sub R, right? For all permutations on R symbols. Okay. And 2, it's completely antisymmetric. If T of V1, V2, VR is equal to the sine of sigma times T of V sigma 1, V sigma 2, V sigma R for all sigma in sigma R. In both of these, for what? For all V1, V2, VR in V, right? Of course, we're assuming here that T is a mapping from V cross cross V to the reals, and there's R fold of these.
So, does that mean that it can be completely symmetric and anti-symmetric at the same time? Because what if the sign is positive?
But it has for all sigma.
Oh.
For all sigma. So like, example 2, So let me circle back to my determinant formula, all right? So like you could define the determinant of, let's say, you know, V1, V2, Vn, where here V1 through Vn are elements of Rn, they're just column vectors. You could define that to be like the sum oh, curses. I don't know if I know how to write the formula down in permutation. Good grief. All right. Rats. Just a second here. I'm going to have to give you, here's my definition, so I'm going to start with that. I1 through In, 1 to n. All right. And then we've got epsilon, I1, I2, In. And then I've got like V1, I1, V2, I2, Vn, In. This is my formula for the determinant, my definition. But mathematicians oftentimes like to write this in terms of sum over permutations. So what would this look like as a sum over permutations? It would look like the following. It would look like the sum over sigma in Sn, because here we're permuting n things, yeah? So sum over permutations of the sign of sigma, and then you just got like V1, the sigma 1, V2, sigma of 2, Vn, sigma of n. And you can see now that will reproduce, well, of course you could also see how to write the cross product now in terms of the sum over permutations on three things. By essentially the same trick, like I could rewrite my remark, I could go back to my remark and I could write the cross product as a, you know, a sum over permutations of three things if I wanted to, where the plus or minus is given by the sign of the permutation. But anyway, so there's that. All right, so let's talk about the wedge product then. I don't know if I have any other examples to share here. I don't think I do. I think it's just mostly that. I talked to you already about how we can decompose a bilinear map into a symmetric and an anti-symmetric bilinear map, right? But let's see here. All right. Sorry, I'm thinking about what's the best way to proceed here. Okay. So I give a definition on page 193 where I just define the wedge product of p dual vectors. So we'll go with that, okay? Definition. E I1 wedge E I2 wedge wedge E IP. All right. It's going to be the sum over sigma in the permutations of p indices. All right. Well, anyway, sum of p permutations, and we put the sign of sigma, and then we do E to the I sigma 1 wedge E to the I sigma 2 wedge. Good grief here, come on, seriously? I'm going to define the wedge product in terms of the wedge product. Good job. Good job. Yeah, no. I want tensors there, right? Tensor. Tensor, 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 tensor. Keep in mind, we've defined the tensor in a previous lecture. How did we do it? We defined it in terms of it being a multilinear map, right? So like, the tensor product of p-fold dual vectors would be a type p0 tensor. Okay, so this defines type p0 tensor on V. All right. So it's the completely anti-symmetrized tensor product of the dual vectors. And I'm playing this game here that I'm giving you indices here. So I'm not on a p-dimensional space, right? I'm on an n-dimensional space. I'm just taking p dual vectors from n-dimensional space. There's a kind of conflation of two concepts up here, see, because the dimension of the space is n, and the number of things we're anti-symmetrizing is n as well. All right, example 2 is special in that regard. So that's it. That's the wedge product of dual forms. Now, the interesting thing is we can extend this concept first of all to let me see if I have a definition proper set down in here anywhere. See, there's two different ways to attack this. The one way to attack it would be to all right, so my exterior algebra I have in the next section. I guess I'm going to resist my urge to define the exterior algebra right this second, and we're just going to sit and fiddle with this definition for a minute or two to understand it better, okay? Let's do that.
Is there any reason why you use the vectors in the basis, dual vectors?
For E? Just a letter.
No, but I mean, is there any reason you're using the vectors in the dual basis instead of arbitrary vectors for the definition?
Well, yeah, because we take the wedge product of differential forms typically, and differential forms are naturally built over the cotangent space. So it's because we ultimately build differential forms with differentials, which are naturally viewed as dual vectors, whereas the partial derivatives are the vectors.
But I mean,
so
you're using the vectors in the dual basis instead of
yeah.
the dual vectors, like arbitrary vectors.
Oh, why am I doing the basis ones?
Yeah.
No reason, really. You could do it you could just as well erase the e's and put alphas in their place. Fair enough. That's a good question.
Just to have it more general.
Yeah. There may be more than that. It may be that I'm thinking, maybe that this discussion originally stemmed from a concept of defining it on the basis and then extend linearly off the basis. That may be the reason historically that I started with this. I mean, this whole discussion is going to drive algebraists mad because, like, it's trying to build a forest from trees. Like, maybe, you know what I mean? Like, you could just define the wedge product more like abstractly and then show that you can find these objects inside that. I'm going the opposite way. I'm building the objects and then putting them together to build the exterior algebra, which is not, from an abstract algebraic perspective, the greatest thing, for sure, okay? Let's look at this, though. So if we have three things, and you know what, Ernesto, I will take your advice and forget about my basis for a second, but if I had, for instance, alpha, wedge beta, wedge gamma, then, you know, I would do something like, oh, rats. See, I kind of have to enumerate them to follow this instruction here, don't I? So I guess I have to think of this as alpha 1, wedge alpha 2, wedge alpha 3, right?
Can you just say gamma
sigma
Alpha
of,
to beta.
well,
Well, I guess we define that as
so,
in
yeah, I don't know, but, so here, let's say we'd have, you know, the sign of just the identity permutation, and then I'll stick with the numbers for a second, okay? It hurts me to write these, but I'll do it. All right, then plus the sign of the permutation 1, 2, 3, perhaps, right? And that would be 1 goes to 2. So I've got what, alpha 2 wedge. Oi, 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 oi. Now I gotta think. One, two, three. 1, 2, 3. So 2, 3, 1. Alpha 2, alpha 3, alpha 1. Plus the sign of my other even permutation, which was 1, 3, 2. And that produces the pattern 3, 1, 2. And then I've got my odd permutations, like the 1, 2. So I got alpha 2, wedge alpha 1, wedge alpha 3, plus the sign of 1, 3, where that flips the 1 and the 3, so the 2 stays alone. So I've got alpha 3, wedge. Good grief, I've got wedges everywhere. These are all what? They're all tensors, right? I did it again. I'm a dummy. Just a second here. Let me fix my mistakes, of which there are many. Tensor, 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 tensor. All these are tensors. All right, getting to the point, eventually. We've got what? We've just got alpha 1, tensor alpha 2, tensor alpha 3, plus alpha 2, tensor alpha 3, tensor alpha 1, plus alpha 3, tensor alpha 1, tensor alpha 2, minus alpha 3, tensor alpha 2, tensor alpha 1, minus alpha 2, tensor alpha 1, tensor alpha 3, minus alpha 1, tensor alpha 3, tensor alpha 2. And if you're wondering how I came up with that, I wasn't actually looking at my previous step. I was just thinking through the cyclic permutations. Like basically 1, 2, 3 is there. That gets a +1 because it's the identity permutation. And then I just scoot the 2 over and move the 1 over to the other side. And then I scoot the 3 over and move the 2 over to the other side. And then the opposite way, 3, 2, 1 is an anticyclic. And that then, if you, well, anyway, that's an odd permutation. And so I can just, like that, yeah. Yes. Is good? So you could write the formula for the wedge product in terms of three things, in terms of the antisymmetric symbol on three things. You know, I could write this with an epsilon ijk formula if I wanted to. If I don't like permutations, I could just as well express it like this, right? Alpha, wedge, beta, well, and of course, to really go back, I should change my betas to, you know, alpha 2 is beta, alpha 3 is gamma, you know. But anyway, if I was to write a formula like this, say alpha 1, wedge alpha 2, wedge alpha 3, I could just write it like this. The sum over ijk, right, epsilon ijk of alpha, alpha I, alpha j, alpha k. Of course, I am missing, as seems to be my custom today, the tensors. Because that would give you the same thing. It would give you 1, 2, 3, 2, 3, 1, 3, 1, 2, and and then minuses on the 3, 2, 1, the 2, 1, 3, the 1, 3, 2. That would be the same. That's another way to write the formula. If you don't like permutations, right? If I was teaching this to sophomores, I wouldn't use permutations. That's gibberish to them. But this is a formula in terms of integers, plus or minus 1 and 0. That's very easy to understand, actually, with a little bit of investment. Although mathematicians, they are scared of this. This they do not like. Well, 20th century or 21st century mathematicians. 19th century mathematicians knew about this and loved it, and wrote telephone books espousing its virtues, because that's just determinants, is what that is. All right, are we good? So if we have a wedge product of 4 things, then that corresponds to an anti-symmetrization that has, so you notice that 3 factorial has got 6 terms. If you had a wedge product of 4 dual vectors, you'd have 24 terms. 4 factorial is 24. Wedge product of 5, you got 120 terms anti-symmetrized, right? What's cool is that we can extend the wedge product to wedge together to different, we can take a type P0 tensor and a type, I need to introduce some language here, so let's get to it. So this is the section 9.3.2 on the exterior algebra, and I suppose I should mention that we have a notation for completely anti-symmetric. So like definition, the completely anti-symmetric type P0 tensors on V are called I guess they don't give them a name. I would usually call it a P form. And lambda upper P of V is the set of all such tensors. If T is an element of lambda PV, then we can express T is equal to, well, how's it go? It is the sum over, I1 da 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 IP of T I1 da 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 IP of E I1 tensor E IP. But we can rewrite that as the sum over all indices I1 through IP equals 1 to n of like 1 over p factorial, all right, T I1 da 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 IP of E I1 wedge E I2 wedge EIP. So to explain that, it's really relatively simple. What's going on is that if you think about this, if it's going over all indices, I1 through IP, and there's P of them, they're oh, how can I say this? Well, let me just focus on the right-hand side. If we think about what this means, right, it's that completely anti-symmetrized sum of tensor products of these dual vectors, right? And so there's like p factorial terms here, right? But every last one of those can be rearranged to this, right? According to oh, rats. I forgot to discuss something. Yes, I forgot to discuss something. Yeah, I'm sorry. I've jumped the shark here or whatever. Whatever you want to say. I need a lemma to make sense of this. The lemma I need. Sorry, I should spend some money and print my notes out. But anyway, the lemma I need is simply this. This, if I do EI1 wedge, EI2 wedge, da 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 wedge, EIP, that's equal to the sine of sigma times e to the I sigma of 1 wedge e to the I sigma of 2 wedge da da wedge e to the I sigma of p. So like I suppose it's probably easy enough to prove that lemma. Probably we can just go back to the definition and think about it. I think that's probably how this is proved most efficiently. So of course, on the one hand, this is all right, fine. I made my bed, now I gotta lie in it. So by definition, this is what? The sum over tau in the set of permutations, P, right? Of E, I, tau 1, wedge, right? E, I, tau of 2. I keep doing this. What is it? Tensor. And what else? What am I missing? The sine, yeah. All right, on the one hand we have that. On the other hand, over here, we have what? This is the sine of sigma, right? Times the sum over delta, let's say, in the sum of the permutations, right? Of E, my bad, I did it again, sine of delta, right? Sine of delta, and then E to the I delta of sigma of 1, tensor e to the I delta of sigma of 2, tensor tensor e to the I delta of sigma of p. All right? So that's what that side would be. All right? But I would point out that this we can rewrite as the sum over delta in sigma p of, now check this out, sine sigma times sine delta. Remember this property? It's a homomorphism. The sine is a homomorphism, and it goes from, it preserves the composition of permutations to the product of the numbers 1 and minus 1, right? So in other words, this is actually the same as the sine of the composite of, I was supposed to have a delta here. I'm a dummy. Of delta composed with sigma, right? Or we'll just write delta sigma. And then I've got, e to the I delta sigma of 1, tensor, tensor e to the I delta composed with sigma of p. At this point, we appeal to a somewhat well-known but annoying combinatorial claim, which is that if you have a sum over all possible permutations, then this summation over sigma or delta is, I can just cross that out and say, oh, well, this is the same as the sum over that. Basically, I make a substitution. So, because this sum was over arbitrary delta, so it's the same as saying it's over arbitrary delta sigma. But then what's that? Well, just let... Yeah, you just say tau equals to delta sigma. Yeah. And then we're there. And then we're there, which means we have equals. The circle is complete. Yeah, but there is something there. But once you have that lemma in hand, you see, I can take this, right, and I can permute it to that. Let's see here, how can I say this? All right. Son of a gun. How to say this? Most of these terms are 0. Most of these terms are 0 because if it's completely antisymmetric, only the distinct index terms survive. And of those, so you've got distinct index. You can rewrite this as like a sum over, oh, I lack the words. Goodness gracious. I mean, we proved this for 2 things. Let me see if I've got some wisdom in the notes that I have forgotten at the moment. I'm just missing something to say here. Oh, in the notes I had the good sense to interact with the wedge product on some sets of vectors, So like I would encourage you to read page 194. Okay. Because I didn't quite get to that way of thinking here today yet. All right. Yeah, 194 has got some nice calculations where I just I feed a wedge product of one forms, I feed them like a triple of vectors and show you what the formula is. That's kind of nice. I mean, what I do there is I show you that that formula, that definition over there on the other board actually does produce an antisymmetric. It really does produce an antisymmetric. I haven't proved that. I have not proved that this is a completely antisymmetric P0 tensor, right? I just wrote this formula down and claimed it. I haven't actually showed you that if I feed this, you know, a p tuple of vectors, it actually has that claimed antisymmetry, right? That's we could talk about that. I'm just stuck on this formula at the moment. All right, so all right, fine. Let me just work it out. Just work it out. So what was our formula for T? Ti1, I2, da 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 IP. Well, that's equal to T of what? Of EI1, EI2, da 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 EIP, right? That we had that from the other day, yeah? Agree?
Yes.
Okay. And so if this is completely antisymmetric, right? Then this is equal to the sine of sigma, right? Times what? Times T of EI sigma 1 through sigma P, right? Which I'll just skip and say, well, that's the same as, fine, EI sigma 1, EI sigma of 2, EI sigma of P. All right, great. But that, of course, is what? Sorry, I'm just having trouble. I have to think about these index up here, right? But what's going on here is 1 is less than or equal to I1, I2, da 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 IP, and these are less than or equal to n, right? All right, so sorry, I'm getting hung up on the combinatorics is what's going on here at the moment. So if this is completely antisymmetric, by the way, the other thing I haven't defined today, I should have though, is that good grief. What happens? What's our? Oh man. I'm sorry. I feel like I'm missing something big here. I need sigma, I need to understand sine of sigma is 0. If there's any repeats, right? So this calculation is only legit provided what? I1, I2, da 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 da, IP, distinct. They have to be distinct for me to even do this. Because otherwise, well, that's not true, right? If they were, I could still do this actually, even if the I1, if EI1 was equal to EI2, I could still do this. It's just that for other reasons, I know that that's going to be 0, right? you understand why if there's a repeat, it has to be 0 because we have, like, if it's antisymmetric, that means that we can interchange the inputs, and that would mean that it's antisymmetric with respect to that change of indices. So the non-zero components, the non-zero tensor components to T have to be those ones with the distinct indices. So I really should rewrite this sum in terms of distinct indices, right?
But why do they have to be distinct?
Well, they don't have to be. They could be 0. I mean, excuse me, they could be repeated, but if they are, then that's just 0 because this is 0. So I guess we could rewrite T as T is equal to the sum over, I1 IP distinct, and then what can I do with that? Well, if they're distinct, then I can order them, right? Like, the thing is, this sum doesn't have them in order. This allows for all possible orderings, right? But I'd like to relate that to the sum over, say, I1 less than I2 less than IP. But, all right, so if you think about that, suppose, the thing is that's not the only possibility in here, right? Every single possible reordering of these, of which there are how many? Exactly, there are p factorial rearrangements of that. And so if sigma is such a thing, so like suppose that these are distinct, right? And then if you look at, T of I sigma of 1, I sigma of p, e to the I, sigma of 1, tensor, tensor, e to the I, sigma of p. Well, if I want to, this right here, right, that is equal to the sine of sigma times T I1 IP. So if I group all of the terms here that have this distinct p-fold selection of indices, I'm picking up exactly the tensor products that have the weights given by the permutation, the sign of the permutation that rearranges these p distinct indices, which is to say that what I put here is simply Ti1, I2, IP, EI1, wedge, EI2, wedge, EIP. And then you might ask, but the formula you have up there has I1 through IP ranging from 1 to n. How are those the same formula, right? And the answer to that is